be a registry or a control circuit or any other electronic circuit. This may result into memory corruption, but since the component is not hardly or severely damaged, the software may continue running smoothly until it reads from the part of the memory that was corrupted. So, evaluation of commonly used CPU revealed that half of transient faults may cause calculation error or program crashes. So, either the circuit or this program must be protected. In my research, we choose to protect the program, and precisely the program we are talking about here is the operating system. And the approach we choose is to control the operating system execution through a virtual machine. This leads to this architecture where we have a hypervisor running directly on the hardware and allow us to control the guest OS. The hypervisor we are using is a combination of Nova and the G-Note software with the use of virtual bus to control the operating system execution in guest machine. The general approach is to rely on existing hardware detection and recovery mechanisms like machine check architecture, memory protection facilities, error correcting codes, and errors which may remain undetected by hardware mechanisms. We rely on double execution with comparison of short processing elements which last at most 200 microseconds and are executed atomically. The problem now here is how we handle the coherency of the system and the performance impacts while we are executing redundantly the sequence of instructions and in the presence of external interrupts, which are asynchronous events. The software to be protected here is divided at runtime in short processing elements. A processing element is, as we said, a sequence of processed CPU instructions that are delimited by either a maximum number of instructions. We detect this by triggering the performance monitoring interrupt. The processing element may also be delimited by system call, CPU exception, like page faults, general protection faults, or tax state segment errors, this kind of exception. Also, we stop the processing element when there is input-output instruction, or a process switch, and later we'll also rely on virtual machine exit to stop the processing element. So all these events trigger processing element stop so that we can re-execute them, compare the two execution, and detect if there are transient faults or not. Okay, so concerning the external interrupts, we distinguish two classes of external interrupt. The first class is performance monitoring interrupts. This interrupt is used by the hardening model to stop the processing element when a specific number of instructions is executed by the CPU. And this interrupt has to be handled immediately. The second class is all the other external interrupts. These interrupts cannot be part of the processing element. The handling is delayed when they arrive. If they are triggered, we queue them. So they are queued for deferred servicing until the processing element is finished. So when they arrive, we unqueue them, we execute end of interrupt, and after committing the current processing element, we dequeue all recorded interrupts in first in, first out order. So a special care must be taken when doing this. A special care must be taken regarding real-time processing. If the interrupt requires immediate servicing or it is proved not influencing the processing element idempotency, we may service it directly or immediately. But if it cannot satisfy this criteria, we face this in this way. We face a that case where we cannot handle this kind of interrupt now. So we test this approach on Genode system with its microkernel Nova, and during the booting phase, which lasts about 600 CPU gigacycles, approximately 4 minutes, with no idle loop, we noticed that 99% of all timer interrupts are delayed, whereas all other interrupts, we've also all other interrupts. So it is the busy time, and all interrupts that were triggered during this booting phases are delayed. But especially timer interrupts were delayed with in average 18 microseconds. All other interrupts, like keyboard or other global system interrupts, were delayed with about 40 to 50 microseconds in average. So this was the case when the system was booting. When the system, after the system boot completely, we let the system run with idle user, and the overall result was that only 20% of timer interrupts were delayed, whereas none of the other interrupts were delayed. So this is quite optimistic about performance with dual execution of processing element, because the current implementation is largely improvable, and all the system after it's finished will run in after booting phase completed. So, in conclusion, we may say that when executing redundantly sequence of instruction of piece of software, interrupt management is a key aspect to performance. Here we choose to delay the servicing to ensure that the two executions are the same. We investigate how interrupt delaying performance impacts on the system, and we found that in general, this will not impede the operating system dual execution in normal execution. So that's the conclusion we brought in, and that's also the end of our presentation. Thank you for your kind attention. Any question or suggestion are welcome. Thank you.
Thank you. So we may have some questions here. Yeah.
So it sounds
okay.
like a processing element might be restricted to something that executes on a uniprocessor system. How does this work, or does this even work in the presence of concurrency on an SMP system?
I don't get you. I don't hear you correctly.
Yeah, maybe it's a large question. Maybe it's better if we...
Okay, can you hear me?
Yeah, I hear you. Yeah.
Okay, it sounds to me as if your processing element is a unit that only works on a single processor system, because if that's right? It doesn't work on SMP.
It doesn't work on
I didn't land of the question.
Yeah, the question is coming now.
Okay.
The question is, does the split of the program into processing elements work on an SMP system where you have concurrency also due to other processors, not just interrupts?
I suggest we write the question because the sound is not correct here.
Okay, it's too hard. Maybe the question was if this is working for SMP systems. Yeah. Is your concept working for SMP systems? Is the question.
Okay. So right now it's not already running on SMP processor, we do not consider multi-threading now, so this will be a part of future work. So now all consideration about multiprocessor are left for future investigation.
Okay.
Did you get me?
Yeah, we are. Okay, have a question?
Okay,
Yeah.
thank you.
I think it's highly dangerous to delay and interrupt until after 200 instructions have elapsed, because in the worst case you have a sequence of instructions where you have interrupts disabled, then you have a small window of say 20 instructions where interrupts are enabled, and then you disable them again. And if sort of that region falls completely into a PE block, you will never be able to inject it.
Okay, can you shorten this question? or maybe you come in front and talk directly? Yeah, maybe he sends you an email. It's another large question. Okay, other questions? Okay. Seems not to be the case, so you two get in contact. Maybe.
Okay,
And yeah, thank you.
thank you too, and we'll see you next time.
So, so see you later.
See you later. Thank you.